that was early 2017. And since then, he has worked on a number of topics, not just those that he's going to talk about today. So his PhD work resulted in, I would say directly, he's going to talk about 4 of his papers, high quality journal papers today. But outside of this, he's also published 5 or 6 journal papers in collaboration with faculty members all over the world. So he's been exceptionally productive. And I must say, we're all proud of our students. There are some students who, need close advising. There are some students who run with any ideas you have and make them better. But Shaowu is very rare. He takes half-baked ideas, bad ideas, and finds a way to make an elegant question and comes up with an elegant solution. And he goes end to end. He looks at the algorithms, he looks at the math, and then he looks at applications. He's also very rare because things that are simple for most of us are hard for him, and things that are very, very hard for most of us, come naturally to him. So I would say I have to point that out. But without further ado, I think we should get started on Shaowu's dissertation. And for the non-UM people, the way this goes is Shaowu gets about roughly 50 minutes to present his work. And if there are very pressing questions during his dissertation, during his talk, I think it's best if you ping me. You raise your hand or you ping me so that I can act as moderator, because we have about 50 people today. And there are also faculty members from Michigan and elsewhere outside of the committee that have joined in. So very warm welcome for taking the time. And then at the end of the talk, we're going to have an open session for audience questions. And following that, Shaowu spends about half an hour, 1 hour with the committee. So the committee questions him, and then a decision is made. So again, as I said, Shaowu, we don't expect too many questions during the presentation, but if there are pressing questions, please email me, please message me via private chat, and it's perfectly okay to do that. And Shaowu also said he's going to stop at strategic moments during his talk. He's going to stop 3 different times after some of the major sections of his talk are over. And that'll be another opportunity for you to ask quick questions if you have any, but please ask your questions through me. But the committee can ask questions at any time. They don't obviously have to go through me. They can just jump in and ask a question at any point. So anyway, a reminder, so about 50 minutes will be reserved for the talk, and then how many other public questions we have, and then we're going to get into the committee questions. So that's the plan. And before we get going, does any committee member have any question or anything to say? If not, we can get started. All right, if not, let's get started. Shaowu, get ready to share your slides. I've just made you co-host, so you can take over.
Yes. Can everyone see my screen? I think so. Can you see my screen? Okay.
Yes, we can.
Okay,
go ahead.
Awesome. Awesome. Good morning, everyone. Thank you, Karthik, for the introduction. Good morning, everyone. My name is Shaowu. Today, I'm going to talk about my PhD thesis on robust and interpretable learning for operator-theoretic modeling of nonlinear dynamics. In this talk, I will go through the backgrounds on the existing challenges in modeling high-dimensional system, and why Koopman operator is a promising approach and state-of-the-art in approximating Koopman operator. Then I will go into 3 of my major contributions in the thesis, which involves theoretical and numerical aspects, as well as applications. Okay, so we're living in an era of technology in aerospace engineering that is advancing at an unprecedented rate in order to keep up with our ambitions in conquering the sky. High-dimensional complex nonlinear dynamics are unavoidable in most of the cases. To address the associated questions, we need a deeper understanding of the increasingly complex multiphysics problems. We need more accurate models of complex physics. We also need robust and efficient control strategy in a challenging environment. So there are many challenges in the existing high-dimensional nonlinear systems. On the right figure, arising from a Navier-Stokes equation for fluid dynamics. For example, traditional high-fidelity tools based on first principles are intractable in the design process. Traditional high-fidelity tools based on a traditional flow field analysis tool are mostly a priori rather than being predictive in a posterior sense, which is important for modeling and control. Standard non-intrusive ROM do not have uncertainty or stability guarantees, and classical optimal control techniques are locally optimal, and many techniques use local linearizations. On the other hand, we almost know everything about linear systems, such as stabilities, predictions, observability, controllability, and how to design optimal controllers. An intriguing question is, can we transform nonlinear systems into linear ones? Take a look at this 2D nonlinear system, for example. If we transform X into phi, we end up with a 3D linear system. Intuitively, such eigenfunction observes all the nonlinearity so that what's left becomes linear. If we eigen-decompose the linear dynamics, we effectively decompose the original nonlinear dynamics. Such a linear embedding process is supported by the Koopman operator theory, which generalizes the local linearization of nonlinear dynamics to global one. The essence of Koopman operator is to find a linear embedding of the nonlinear dynamics. We lift the original nonlinear dynamics with a mapping G. Then in the Y space, the system becomes linear, and the result of the action on the Koopman operator leads to the evolution to the next time t plus delta t. With the above, it is now easier to introduce Koopman operator formally. For any function defined on the manifold, Koopman operator would tell you how would this function evolve in the future according to the nonlinear dynamics. So Koopman operator is a linear operator, so we can have a spectral expansion. Consists of time average, point spectra, and continuous spectra, which resembles the famous triple decomposition in interpretable theory. However, the nature of Koopman operator is hard. It is infinite dimensional, and the continuous spectra arise from the chaotic system forbids any accurate long-time predictions. Therefore, for practical purposes, we consider learning the point spectra of Koopman operator, which reduces the problem to searching a finite dimensional invariant subspace. So at this moment, you might still wonder, why do I need Koopman operator for modeling control? So first, the linearity enabled by Koopman operator allows one to leverage many fruitful results from the rich linear system theory. Second, searching Koopman operator can be purely data-driven, so it applies to a system where it's challenging to even obtain the first principle models. Third, Koopman with model predictive control converts the non-convex problem into a fast global convergent convex problem. This is strongly desired to implement MPC in real time. Fourth, stable Koopman framework, which I will talk about later in this talk, is the only known reducible modeling framework that guarantees temporal stabilization for general nonlinear dynamics. However, first, Koopman operator, learning Koopman operator requires data at the most of the time. Second, currently it is unclear for a data-driven Koopman operator on fully chaotic system where continuous spectrum needs to be considered, but however, it is not very practical for modeling and control. Existing approaches in approximating Koopman operator have several issues. So one of them is using historical features to construct observables, which are called a time delay DMD, or sometimes referred to as time delay models. The issue there is that there isn't any non-asymptotic theory for the order of time delay embedding. Not clear on why sometimes it works and sometimes it doesn't work. Second, there's a lack of clarities. In how to extract uniformity and Koopman invariant subsets from data. Typically, one ends up with thousands of modes and doesn't know which one is correct. Third, the existing approaches in deep learning architecture doesn't have stability constraints. Therefore, for example, in their paper, the model arrived as an unstable mode for a flow path cylinder. This is strongly not desired for any long time predictive modeling. Therefore, my goal is to provide new theory and tools to learn Koopman operator with better theoretical insights, more interpretability, robustness, and reliability. So yes, here let's come to this first topic on the time delay embeddings. So Takings proposed the 1981 first proof on time delay embedding, which says that one can reconstruct the whole nonlinear system from the history of perhaps quite limited measurements of the system. It is a concept of generic nonlinear observability. It has been applied in deep learning, Koopman operator, reducible modeling, where closure dynamics requires memory. In Takings' theorem, he also provides a conservative number of the time delay required, which is twice of the manifold dimension. However, it has been widely known that it is too conservative in many cases. So how much delays do we really need to construct the system? So in order to answer these questions, we need to first fix the type of model we use. So here we consider linear models, which is basically using past states to linear predict the future state. This is similar to many other models, for example, the ERA, autoregressive, vector autoregressive, single spectral analysis, and Havyuk, and most importantly, it has connection to the time delay DMD, sometimes referred to as Hanker DMD. However, the existing studies only has convergence on approximation to the ground truth for our ergodic system, and most of them are studies are empirical based. So here we study our analysis by assuming a noise-free periodic limiting circle, but this can be easily generalized to quasi-periodic attractors. So our broad question is, what determines the minimum number of time delays so that the model becomes very accurate? What is the influence on the time delays on the conditioning of the model? And is there a partial period of data sufficient to predict the entire period? And would there be implication for applications? So for the scalar cases, we have we come up. So basically, we project the trajectory data into Fourier space, and we analyze the random matrices come out of it. We found that the number of jumps basically in your Fourier spectrum determines the minimal time delay you have. And further, we analyzing. We actually can find an exact expression for the Koopman Koopman operator. Basically, we find turns out to be the location of the jumps rather than amplitude determines the Koopman operator based on our assumptions. So let's take a look at how this actually works in a numerical example. Let's take a toy example. So first, of course, when you're collecting data, you have to satisfy some minimal sampling frequencies for an of course sampling theorem. Then let's start and look at these simple nonlinear systems. From the theory, we analyze the Fourier spectrum. It turns out to have 10 jumps for the first component and 18 for the second component. So accordingly, the number of time delays is 9 and 17. So this matches very well with our theory. So basically what we do here is just sweeping along for the number of time delays, and we compute the posterior error corresponding to between the model and the truth, and then you have this plot. So if you do a further analysis, you can show that the minimum number of data samples you need is basically 2p, basically twice the number of jumps in your Fourier spectrum. However, if you can have a relatively high sampling frequencies, here basically representing number of samples for each period, your time delay DMD model can look like extrapolating future. Again, this is look at this right figure here. The green part is corresponding to the number of training data you have. You just need at least this little training data, and you apply a time delay DMD, you are able to reconstruct the full system very well. So this is actually not a magic. If you look at the thesis, it's quite straightforward, and we explain the extrapolative results from previous papers. And for the vector cases, the situation can be a little bit complex. So basically, let's say it turns out that there's an interplay among the Fourier coefficients that will complicate explicit derivation of minimal time delays for vector cases. And it turns out the number of minimal time delay you need is related to an output controllability index of an induced linear system. And however, we come up with a geometric interpretation for explaining the whole thing. Is that, let's say you're starting with a constant vector, it's like 1, 1, 1, 1, and in this m-dimensional space, then you rotate this constant vector with matrices determined by your sampling frequency, and then you rotate m minus 1 times, and then project stretch rotate with all the Fourier components you have. Note that the a superscript here corresponding to the Fourier spectrum of their component. And then you have this sort of a blue hyperplane, and this is a subspace. Then you're starting from this constant vector. Then you rotate L times. L is basically the number of delays in your model. Starting with the orange, this orange bunch of vectors, and then you project stretch rotate with the corresponding Fourier spectrum of each component. End up with large orange subspace. If this blue subspace turns out to be within this orange space, your number of time delays will be able to accurately recover the full system. So as you can see, the larger the L, the larger the subspace you're going to get. So you're getting a higher chance of encapsulating that blue space. So the model becomes accurate. However, you might think, since we mentioned before that if you have a high sampling frequency, you can predict future in time. So why not adding super high sampling frequency? However, this is due to numerical conditioning issues. And let's say for a simple 5-wave, 25-wave problems, you even use half of the period of the data, and you use the correct number of time delay, which is 9, corresponding to 5 harmonic waves. Then it turns out that short-term prediction is okay, but long-term predictions deviates. So what's going on? So the reason is actually because the near colliding nodes in the Van matrix in the model. So however, the remedy is actually quite straightforward. The remedy is actually using more time delays. So we basically showed that, explicitly showed that the condition numbers will monotonically, the upper bound on one condition number will monotonically decreasing with L over M. L is the number of time delays you have. M is basically the number of samples for you for each period. And if the time delays goes to infinity, the condition number actually will converge to 1, which is perfect conditioning. This is not surprising because it's just well known that if you have infinite time delays, the algorithm converge back to Fourier transform. And so more time delays leads to smaller bound on the condition number. Okay, let's see if this is true. So let's see our previous examples. We still have the 5 samples per period, but we double the number of time delays we have. Now we see the prediction becomes much better. So then let's take a look at these details in the implementations. The first is let's sweeping the time delays versus a posterior normalized error. We see there's a big jump. And the error becomes decreasing, and after 17, you can see it's almost around 10 to the minus 4, which is you cannot see a difference from a naked eye. And however, if we look at the least square errors in this process, it's always very small. It's always below 10 to the minus 23, which means what's actually happening, why the period is not working, is because the error propagation in the process. So which is related to the condition numbers. And if you plot the condition number, you see the condition number is dropping with respect to the number of time delays you have. So previously we are analyzing with noise-free data, and how about really applying on some noisy data? Because we have some theory for the condition number, so we sort of know what's going to happen for the noisy case, even though our analysis is based on noiseless case. So let's take a look at this two spectra of measuring the robustness in real-time delay and DMD. The contours here basically tells you if you're given such a disturbance, what's the worst case that the eigenvalue will be deviated from the true eigenvalue. So a true eigenvalue basically in the blue dots here. So as you can see, of course, the larger the control, the less robust of the model you will get. So as you can see, as the time delay increases, passing is L equals 9, which is like a critical time delay, where you can think of it when the matrix at that time becomes square. And then the control shrinks, basically the robustness improves. And let's look at what if we put some real noisy data put into it and see how it performs. So I starting from here, I starting from 100 realization of noisy data, and each noisy data has it will be trained with a model. Then you do eigenvalue decomposition, so you can have an ensemble of eigenvalues. You're sort of having a distribution of eigenvalues. As you can see, as time delay increases, the eigenvalues kind of approaching from the imaginary axis and shrinking, and then becomes quite dense on the imaginary axis. What happens in the predictions is perhaps more straightforward, is that when you increase the number of time delays, the ensemble average, ensemble mean becomes more and more accurate. And even if we have super high time delays, some of the realization becomes unstable. This is because the ground true eigenvalues are on the imaginary axis. So if you have a noise over there, and it can be deviated to the right half plane, which causes instability. However, if you look at the mean over there, the mean actually matches with ground truth very well, which means if you have if you make this model probabilistic and Bayesian, it should perform very well and robust to noise. And however, our previous analysis and demonstration are always on some toy examples. For a larger scale turbulent free simulation, it can be a little more complicated. So the conventional wisdom, when using this model, believes there's a finite rank lower dimensional linear embedding space. And they believe that time delaying works because the large degree of freedom. However, this is not the full picture of the high dimensional chaotic flows. First, there's no finite rank lower dimensional space for the dynamics of the chaotic flows. And second, if you're increasing the larger number of time delays, at some point you actually decrease the degree of freedom because especially for fluid mechanics problem, because when you in your practice, when you're actually doing it, you do SVD, and you say you do an SVD on 100 snapshot, 1,000 snapshot of the simulations, and you end up with 1,000 by 1,000 because the degree of freedom in the fluid simulation is much larger than the number of snapshots you have. This is just because of practical issues in storage. You cannot just store 1 million snapshot compared to if you have 1 million degree of freedom. So then the number of degree of freedom start to shrinking. So ideally, you will want to keep your degree of freedom in your model to be high while still passing this peak point, which I will explain why we need a peak point. So as we're just analyzing the data on a 3D really Bernard chaotic convection, we observe two phases. The phase one is that the condition number increases with increasing number of time delays. So basically, if you're new to time delay DMD, and your advisor asks you to perform a simulation, and then if you are in this phase, you will figure out that you find out time delay DMD doesn't work. It blows up the whole thing. However, if you go to the second phase, you keep increasing the number of time delays, you actually see the error actually decreases. And what actually happens here is the system becomes overfit. So you have more parameters than number of data you have. However, this is a linear model. So when it overfits in least square solver, you have a nice regularization, basically the minimal norm. It turns out to be actually a very good regularization for many problems. And actually, for applications, there will be a reducer modeling for 2D combustion in the series. So for the summary of the part A, I provide a theoretical analysis of linear time delay models of nonlinear dynamics on a tractor. I found out the number of jumps in Fourier spectrum determines the minimum time delays you need. And the minimum time delays in the vector cases is related to the output controllability index of an induced linear system. And I demystified the extrapolation for harmonic waves when it's noise free and well conditioned. And I proved that for more time delays, you're getting periodic neural conditioning, and it will be critical for SVD-induced system of large-scale unsteady flows, and it's verified and validated in applications.
Yeah.
Yes.
Sure, sorry to interrupt, but you're presenting a lot of information very quickly, and because it's the online format, it may be good to take a short break, 10, 15 seconds, whatever, and see if audience has questions.
Yes.
And you can, I think, directly ask, because it's not like there is a big lineup of questions, but if the committee or someone else has a quick question on this part, maybe you leave it in the next slide so people see the outline.
Yes.
Yeah, please ask. This will be an opportunity to ask, or opportunity to take a 15-second mental break also. We all need it.
Yes.
Right, no takers as of now. So yep, you can move on to part 2. So you're doing pretty well on time. So yeah, go ahead.
Okay, thank you. So now I'm going to talk about part 2. The motivations is that I want to searching for accurate and minimal Koopman subspace. The reason why is traditionally for EDMD and KDMD, the main idea is like you span an L-dimensional function spaces with some fixed or implicit features. Then you basically using data to perform orthogonal projections of the action of Koopman operator on this subspace. Then the realizations of Koopman operator becomes a finite-dimensional matrices, because projecting a finite-dimensional function subspace. However, the drawbacks is usually you end up with too much redundant modes. You end up 1,000 modes, usually typically, or hundreds of thousands. And there will be an existence of a lot of spurious modes, which you don't know which one to choose from. And third one, you need to choose the hyperparameters in this process, which actually turns out to be quite critical. So the motivation is that I want to find basically find a minimal Koopman invariant subs which is accurate. And so let's look at this figure here. You have a nonlinear dynamics here, and you have a fixed number of fixed set of fixed nonlinear mappings, which basically maps you into a L-dimensional space. The L is not the time delay imperius, but the number of dictionary functions you have. And then I don't want the full L space. I want a hyperplane in this L-dimensional space that is accurate and able to reflect what's going on in these green potatoes, what's going on in this nonlinear dynamics on this manifold. So this is overarching goals. And the proposed framework is a modal agnostic framework. So the main idea is that first you need to select the top few linear involving modes by performing a posterior analysis on the validated trajectory. Those modes are all coming from the EDMD or KDMD or whatever, or time delay DMD, whatever kind of Koopman approximation you come up with, you can all throw in here, and it will perform the posterior analysis for you. And then you can compute for each mode what is the corresponding linear normalized linear reduction error. Note that the larger the error is, the worse the mode is. Okay, it means this mode is not linearly involving according to that Koopman predictive. And you can also compute the number of modes that are included in terms of the reconstruction error. So then you can come up with this sort of X-shaped plot, and then usually you need to manually select a cutoff, which usually this cutoff is very easy to select. So basically you don't want your Koopman modes to be linearly involving more than 50% of it. And then after selecting all these modes, you put them into sparse selections using multitask feature learnings, and basically it will removing those redundant modes, because some of the redundant modes, most of them are corresponding to constant functions, because constant functions are Koopman algorithm function for any dynamical system, but they are not informative. They are meaningless to reconstruct the state. And we also show some connection to existing work. So for example, if you consider linear feature in DMD, and you consider constraints on the reconstruction matrices when you are doing the sparse learning, and you fit the modes to be the DMD modes, and you only allow to change the amplitude, then our multitask learning algorithm collapse to the famous sparsity promoting DMD algorithm. And Then we also showed that there's a connection to the empirical criterion. Whereas this empirical criterion, we can show that they are basically doing first step gradient, proximal gradient approximation of our subject on the very strict constraint, of course, with the linear features. And then this basically shows that the previous framework, either empirical or sparsity promoting DMD, are suboptimal optimal solution to our framework, because our framework not only we're not actually manipulating the amplitude in the SPDMD algorithm. We're actually optimizing the modes, the Koopman modes. So it's has much degree freedom. So let's look at an example in transient dynamics. So here is a ship airway flows. So you can think of it. This is the ship flying. Is a ship flowing on the sea, and all of a sudden there's a side wind comes from the right, and then you see you basically see the vorticity generated, and I want to analyzing what's the Koopman decomposition for this type of flows, and then we find out that after analyzing these flows, we found this is eigenvalue plot here. So on the near the unit circle, it means the modes are going to be stable and the long time, and we also observed that some decaying modes. So we end up with basically 4 stable modes, but one of them is constant. So we're not going to discuss about it. The other 3 modes are either corresponding to the very edge of the superstructure on the ship, or corresponding to the induced by the Fernal. The last one is corresponding to circulation behind the superstructure, and they all correspond to different frequencies. So let's take a look at comparing our algorithm against the traditional algorithm for a flow over cylinder, which you might have seen before this presentation begins. So we see that our algorithms were able to extract the correct stable Koopman modes. Basically, they are corresponding to the oscillation frequencies in your lift and drag coefficient. And note that a sparse promoting DMD requires 10 times of dynamical information than our algorithm. And if you use a vanilla DMD, it doesn't perform well at all, and it gives you a lot of spurious modes. So in the next slide, you will see our algorithm performs. This is a posterior predictions of the POD trajectory. And the blue one is traditional SPDMD, and the red one is our algorithm. You can see our algorithm matches with the ground truth very well, while the sparse promoting DMD has large deviation, especially near the transient regime. And it is also didn't capture the 6 POD coefficient in terms of the attractor, the amplitude of the attractor. So the reason is that the sparsity promoting DMD using linear features, which is not very suitable for some strong nonlinearity in the transient flows. Okay, and also you can see the initial conditions didn't match well in the SPDMD. This is because the whole algorithm of SPDMD is to modify the amplitude of the DMD, which is corresponding to the initial condition. So that's the reason why they have a way off. So next we compare our algorithm against SPDMD for the 3D ship airway cases. In this case, surprisingly, it turns out that the SPDMD gives 30 out of 56 modes are slightly unstable, and they blow up very quickly beyond the training horizon, and they all cluster near the near circle, which is didn't have a well separation compared to the KDMD approaches. So what is the problem? If you draw this previous, X-ray plot where you computing all the linear evolution errors, you find that the SP, if you're using linear features, the dictionary span is very poor in terms of invariant to Koopman operators. However, if you use kernel DMD, you can see a dramatic increasing in the number of modes you have in terms of more closer to invariant of the Koopman operator. So that's the reason. So if you have a poor dictionary, then you usually expect you have a poor orthogonal projection of Koopman operator. Correspondingly, the algorithm values that you get may not reflect the true Koopman algorithm value. So the summary here is that we discovering a minimal Koopman invariant subspace by proposing a unified model agnostic sparsity modeling framework with mode-by-mode error analysis and multitask learning, and generalized optimization analysis that clarifies the connections among multitask learning, SPDMD, and empirical criterion through the lens of proximal gradient method. So we showed that our algorithm, the reason why our algorithm is better than the others. And we also demonstrate that numerically on several transient unsteady flows. Last, we also proposed open source packages for learning the minimum Koopman invariant subspace. So is there any question for the part B? Okay, so I will continue to
10 seconds again to collect their thoughts, and we can proceed to the last part. But you're doing pretty well on time. You're only 32 minutes in, 31 minutes in, so doing very well on time.
Okay, that's good.
All right, move ahead.
Okay. Now I'm going to talk about my part 3, which is structurally infused probabilistic deep learning for Koopman operators. So deep learning for linear embedding is not a complete new idea. The general idea is basically you're trying to find a knowledge transformation, use deep neural networks instead of a fixed number of dictionary functions. The advantages is that there's no need for a predetermined dictionary. So because the feature actually is adapted to the data, and it's easier training for really huge data instead of solving perhaps a distributed least square problem. However, the disadvantage is that there can be a quite expensive training process, much slower than solving a least square in EDMD and KDMD. And essentially, it is unsupervised learning. So the training actually can be more difficult sometimes than the supervised regression, which we have very successful experiences on how to train them. And sometimes they can be stuck at battle commitment. And this is then it actually leads to our much less understanding for what is learning in the training process compared to the traditional methods. So a table of comparisons with previous frameworks, and our frameworks is focusing on using a continuous learning a continuous Koopman operator, and we consider we can have a nonlinear linear reconstruction. Depends on if you do control, you perhaps want linear reconstruction, and we don't consider continuous spectrum, but we consider both uncertainty and stability into consideration. Additionally, we propose a novel hybrid autoencoder framework, which is accurate and exhibits very good convergence properties. So the contribution is it will be a probable stability, physics information, authentic quantification, and a novel deep learning architecture. So for step 1, if you look at how physics can be embedded into the process, is you starting with a bunch of set of candidate Koopman functions, you do the chain rule, and you basically find out this fx replaces the dx over dt. This is where your governing equations can play a role in. And if we know the physics, we basically can sample uniformly over the domain of interest without need to generate the trajectories. It'll be future opportunity for design with experiments. And also it's easier to incorporate non-uniform sample time series data. And also for some non-autonomous system as well. And the step 2 is to enforcing stability in the linear embedding. So so the motivation is that most physical systems do not have unstable Koopman algorithm functions. So of course, you want to perhaps pose a constraint on make sure that all the Koopman algorithm function come from deep neural network has to be stable. The second is that if you're learning a probabilistic distribution of Koopman algorithm functions, you might want to require stability guaranteed formulation, because just recall the previous example we have. If we add a little bit of noises into the system, and if the system Koopman algorithm values lies on imaginary axis, it's very easy for the system to be unstable. Just step one step into the right half plane, and you get unstable result. So for linear probability distribution, we also need something like that, which will be nice. And the solution we provide is quite simple. We just consider a reparameterization of the Koopman operator. Because of the neural network nature, there will be similarity matrices behind and after this, so there will be no loss of generalities. We'll also prove that. And note that this structure can be flexible. Let's say if you have a Hamiltonian system, you want a Hamiltonian neural network. Basically, you're just setting all the diagonal to 0, and you're getting a Hamiltonian neural network. And all the modes has to be stable, and you only learn Koopman eigenvalues on the unit circle. And step 3 is to consider a novel autoencoder. So the main motivation is that the SVD provides a very nice optimal linear embeddings of the linear dimensional reduction techniques. So we believe that the optimal nonlinear embedding should be near the linear embeddings, but with some deviations. So this is how we embedded it. We having the SVD computed from our training data, and we provide a shortcut into the one layer before the hidden the bottleneck layer, and then we have a SVD mapping out, and then you can construct a formulation for this hybrid. And it turns out that it's actually quite useful. This one researchers come to contact us, come from quantum mechanics, and we use our framework. Basically, you see the blue versus the red, which is running 100 realization of dimensionality reduction. And turns out this for their problems, the vanilla autoencoder actually sometimes gets stuck at somewhere, and it's stuck and it stuck forever. And then it becomes deactivated, and it's very bad. And the backline corresponds to SVD, which means they can be performed worse than SVD. And then they come to us, and we provide them a framework, and it actually works pretty robust and well. So they are happy. And step 4 is Bayesian deep learning with the variational inference. So the general idea is you want to if you want to do variational inference for deep learning, you need to be scalable. So that the approach we use is that, let's say this is the true posterior, it's weird, ugly shape, and we have a nice parameter families of functions, and let's say Gaussian function, Gaussian distributions, and we want to find the best candidate in our family that has the closest chaos divergence between these true posterior and our families. And then the problem corresponds to maximize the evidence lower bound, and we use the automatic differential variational inference framework. And here is this setup for hierarchical Bayesian. It's the first row corresponding to this is how it corresponds to two form. One is the recurrent form, where you only need you only need samples in the phase space. The second one is recurrent form, where you have these trajectory data as you want to leverage it. Okay, and this is an example of showing for toy problems where if you're increasing the number of data, the uncertainty decreases. And this is the example on the cylinder flows. The previous cylinder flows are starting from the non-equilibrium, and it becomes vortex shedding due to the Hopf bifurcation. And we compare our framework with with different levels of signal to noise ratio, and our model was able to predict the means actually pretty well and capture the uncertainty very well at the same time. However, if we compare it to vanilla LSTM, LSTM captured amplitude for claim data, but it, as you can see, there are some still some deviations of when it's a transient regime. However, if you're adding more noises into the for the vanilla LSTM, it performs much worse. It has a wrong phase, and it also has over damping for this amplitude. Our framework doesn't suffer from this. Again, you can of course mapping in the back, because the previous POD are not really friendly to fluid mechanics people. Mapping it back to fluid flows, you see our framework matches the mean very well, and you can also see where the uncertainty has in the flow field. Where as you can see, this is how the uncertainty introduced in this flow field. And next, I'm going to talk about the application in data-driven control, and basically using deep learning from the Koopman, then apply to control. So previous works are either on EDMD derivative based, polynomial based, or time delay based approximation method for Koopman operator, then apply MPC and LQR. Sometimes, most of the time, they use the linear assumptions on actuations, which is a pretty strong one, because if you analyze, we show an example later, analyzing for a simpler system, it's not going to be a simple constant B matrix. Well, but if you can argue that it will be desirable if you are doing MPC. So the Koopman invariant subspace can be inaccurate if you're using some dictionary-based method. And another very classical work from Kaiser is that they use SIMD for Koopman invariant subspace, but they introduce input accurately without any model error using for control affine systems. However, they are mostly limited for simple problems because they are using Sindian polynomials. Our approach is to basically using deep learning neural network and to approximate Koopman, then couples with the state-dependent LQR, basically follows Kaiser's approach for introducing the input in the system. Yeah. So the steps are straightforward. First one, you constructing a Koopman operator, and then using deep learning, and then you formulate the infinite horizon LQR in the latent space. And third, you solve an algebraic Riccati equation at each time step. And finally, you just apply the control input. As you can see, since the phi x is a nonlinear function of x, you end up with a nonlinear optimal control. So this is a very two examples where the system at the origin is not stable because lambda is a positive number. And we're collecting some data within -10, 10, and the goal is to basically stabilize the unstable system towards the origin. And we found out that we also did a benchmark with analytical Koopman, because for this problem you can find the analytical expression for Koopman, and it matches very well, and it beats the linearized LQR. And let's see if we're going to take a look at these out of training samples. We're starting at -20 and 20. Sorry, -20, -20. And then it turns out that this model is still able to, very interesting, it's still able to converge to the analytical Koopman results. And if we are plotting the cost function in given the initial conditions on the phase space, so because it's a 2D system, you can easily spend a lot of seeds and running the controller and see how the cost function is. So basically, we find that for linearized LQR, it's behaving really well and near the origin. However, for the outside, this is away from the origin, performs much worse compared to deep Koopman LQR and analytical LQR. So it's a little bit surprised to us that the deep Koopman LQR actually performs the same as analytical LQR, even twice outside the training regime. So next is an example on the 8D robotic arm. This is still a control affine system, and all we need is we're collecting introductory data from a simplified model here. It's an 8-dimensional ODE system, and our goal is to control the robotic arm towards the original zero state for any situation. I know that this is still working on it to be added to the thesis. So we are starting with a deep learning framework on having 128 hidden dimensions. And we prepare the data with carefully designed distribution of initial conditions, which corresponding to real situations of that robot. And the result is testing at choosing at the initial condition not seen by neural network, and this is able to control the system very well. So, however, the computational cost, we want to make a comment on this. So, as it requires a single forward pass of neural network, which scales quadratically according among the number of salient states you have. And you also need solving algebraic Riccati equations, which scales cubically with your latent dimension. However, recent work has been shown that it's possible to solving this in real time if you with careful hardware implementations. So it's promising for, I believe it's promising for flow control. And also you can actually do a lot of tweaks in this first part as well. And so the summary for the part C is that we propose a stable Bayesian deep learning Koopman framework. We have the differential form, which requires the physics informed and no data. in terms of you need a governing equation. And for recurrent form, you need trajectory data. And we also our proposed framework is perhaps the only known stably enforced non-intrusive real-world models. And uncertainty is well quantified in the context of Koopman operator for noisy data, as we have shown, and we beat the vanilla LSTM. And our hybrid POD autoencoder embedded with SVT performs good convergence for a quantum mechanics data set. And we also provide it as open source packages and Bayesian deep learning for Koopman. So summary for the contributions here. So my contribution analyzing first rigorous theoretical explanations on analytical and numerical rules on the number of time delays. And I propose a novel model agnostic machine learning framework to overcome sparsity and accuracy issues in nonlinear dictionary-based methods. And finally, I come up with a continuous time Bayesian deep learning framework with normal stability, constraint structure, and a hybrid POD autoencoder. All of this towards a deeper understanding from the aspects of learning, a better interpretation from the aspects of sparsity and generalizability, a more flexible, robust, and constrained deep learning framework for linear embedding. So these 3 blocks corresponding to the 3 contributions is like first one, delay structure, second one is third one are corresponding to our open source packages. So for some perspectives, these contributions are just only the steps along the journey of finding a truly robust, interpretable operator-theoretic learning for a nonlinear dynamical system. Continuous spectrum is not well addressed in this work, which will be crucial for fully chaotic systems. And operator theory provides a target for the AI to actually go beyond the vanilla fitting. So Koopman is just one example. There are many intersections and interactions, chemical reactions between the mathematics and AI, and they are forthcoming. And data-driven Koopman operators actually, because of that, it suffers less from the common criticism of generic data-driven modeling, which is interpolation, curve fitting among training data. Because the insights from the physics, model analysis, it actually helps construct efficient controllers. And for the future work, I'm planning to do a robust data-driven deep learning Koopman-based optimal control framework with experiments. Because at that time, you need a lot of implementation issues. You need to reduce the latency triggered by using these architectures on deep learning. However, there's a large community in AutoML, active learning, and TinyML solving this problem related to little data and large latencies in neural network in order to achieve real-time flow control. And second I want to do is to developing variants of nonlinear Koopman analysis for extracting coordinate structures. They will need to be accurate, efficient online, and there will be a little bit variance, especially for chaotic systems. Yeah. So finally, I want to thank all my lab mates in CAS Lab for the past 4.5 years. It's been a wonderful journey. And most importantly, I want to thank Professor Karthik Dwarasamy for providing me with deeper freedom in pursuing a lot of research and collaboration with others and a lot of supervisions. And I really appreciate that. Also, I want to thank all the committee members for taking their time revising and looking at my thesis and providing me with suggestions. And finally, I want to thank all the sponsors. I guess this is my defense talk. Thank you very much.
Thank you, Shaowu. My screen just froze. I don't know if people can hear me, but thank you for fitting all of this incredible amount of material into just about 49 minutes. So that's an accomplishment in itself. So I'll open the floor for questions from the audience. This is the public question answer session. If there are any questions, yeah, please go ahead. You're trigger shy, don't worry. You can ask questions. So yeah, Petro, go ahead. Go ahead. Petro Junior Milan. I think you're muted, but I can ask the question for you. So the question is on slide 55 to 56. If you go there, Shaowu. He
Yes.
said, if you understood well, the proposed method well captures the time average flow field,
Oh yeah.
but discrepant
So
data for transient data. Any thoughts on how these methods can be improved to capture transient data in scenarios like fluid and combustion instabilities? So that's the question.
yeah. So I would say transient data definitely gonna capture very well. But I think the key issue here for because you know that I didn't address continuous spectrum carefully. I didn't address continuous spectrum very well. So this framework, although it still can be applied, you can just throw data into it and see how it works. But it's not going to have a perfect predictions. For a chaotic system, because we all know it's impossible to have long-term prediction. But for short-term predictions, I didn't show it in this slide, but others has tried to apply it for a chaotic system, and it performs better than the state of the art. I would say the vanilla LSTM, not the state of the art anymore, I guess. Yeah. So it can be applied, but in terms of short-term predictions, it will be predictive.
Yeah, I don't know, Petro, if that answers your question fully. But Shaowu, I have a follow-up. So can you talk about how you may extend these kind of approaches to also capture the continuous spectrum?
Yeah, so I'll probably I'll probably go and start with this paper from let me see the paper from Hassan Ababi. He has a study on post-transient flows where he extracting the continuous spectrum from the data, and it actually shows that it's actually turns out to be a problem in signal processing. It overlaps with a problem in signal processing. So you can use a wedge method to extracting the continuous spectrum to dealing with that. So basically, he first find out the discrete spectrum, then filters everything else, and then put it into a wedge algorithm to figure out what's the continuous spectrum. But there's some issues, I would say, in terms of do we really need explicitly dealing with continuous spectrum for a model in control and a modeling and control, or we just probably just throw the chaotic data into Koopman with point spectra that has predictability. So yeah. It's still not very clear for me. Maybe I should do more on that and see if there's some evidence, strong evidence that supports me from one or the other.
Yeah, we'll maybe talk more during the closed session. But I do want to add to the end of that answer that transient flows is not necessarily a problem, but yeah, truly chaotic flows, that's a problem in the current approach. All right, any other questions? Again, you don't have to reach out through me, you can shoot a question. And even if it's simple, don't feel shy. I mean, I'm getting some comments, but not so much on, I'm just getting a lot of compliments, not so much on the questions. Right, we'll give people maybe a minute or two because the committee anyway needs a short break. So I'm going to keep the question session open for another 2 minutes if people want to come forward and ask a question.